All right, so today we're going to be looking at something pretty interesting.
Yeah.
It's a paper called A Computer Vision Problem in Flatland. And
Ooh, Flatland.
I know, right? It sounds kind of like a sci-fi novel or something.
Yeah, definitely.
But it's actually a paper about geometry and computer vision.
It really highlights how a simple problem can lead to some really complex and interesting math.
Yeah, exactly.
And it has applications beyond just robots in a two-dimensional world.
Yeah, so the paper asks this really cool question.
Okay.
Imagine you have a robot and it has a camera, but it lives in this completely flat, two-dimensional world, like Flatland.
Okay.
And the question is, can you have two different sets of points in this world that would look exactly the same to the robot's camera, even if the camera's in a different spot?
So different points, same image.
Yeah.
Okay.
Yeah. And you know what's really interesting is that this isn't just some theoretical puzzle. Understanding how different viewpoints can create the same image is actually super important for things like 3D reconstruction.
Oh, for sure.
Which is used in everything from self-driving cars to
augmented reality.
Augmented reality, yeah. So it's kind of like how the same object can cast a different shadow depending on where the light is.
Yeah, that's a great analogy.
So
it is. The paper digs into this idea and finds that,
okay,
you can definitely have different sets of points that create the same image, but only under very specific conditions.
Gotcha.
The key is that these point sets have to be projections of a common set of points in 3D space.
Okay.
It's like they're all shadows of the same hidden 3D object.
That's pretty trippy.
Yeah.
Okay, so the camera position really matters.
It does.
And in fact, the paper talks about something called the camera centers variety, which...
Whoa, fancy.
Yeah, it sounds very technical.
It's a fancy math term.
Yeah.
But it's actually a pretty simple idea.
Yeah.
Once you break it down.
Okay.
It's just the set of all possible places you could put the camera that would still create the same image from those point sets.
So it's like a map of all the good camera positions.
Exactly.
Okay.
And the paper shows that as you add more points to the mix, the number of possible camera positions starts to shrink.
Okay, so it's
the more points you have,
the
more restricted the camera becomes.
A delicate dance between freedom and constraint.
I like that, yeah.
You know, all this talk about cameras and projections is making me think about how fundamental this stuff is to computer vision.
Totally.
We take it for granted that computers can see and interpret images.
Yeah.
But there's a ton of complex math
so much
going on behind the scenes.
Absolutely. And this paper builds on a whole history of mathematical ideas that have shaped our understanding of how images are formed and how we can extract information from them.
Right. And so
actually, to really appreciate what this paper is doing, I think it'd be helpful to rewind a bit.
Okay, yeah, let's do some time traveling.
Yeah, let's go back in time.
Where should we start?
Well, to lay the groundwork, I think we need to go back to the late 19th century with a mathematician named Alfred Kempi.
Right.
He was a real pioneer in understanding the invariance of points in projective geometry.
Okay.
And invariants are kind of like the DNA of geometric objects.
Oh, okay.
They describe the essential properties that don't change even when you move or project the object.
So Kempi was figuring out the fundamental rules of how points behave under projections.
Exactly.
Okay.
And he developed this really neat way to represent these invariants visually using something called bracket monomials.
Bracket monomials.
Yeah, these brackets basically capture the relationships between pairs of points.
Okay.
And they hold true no matter how you transform the points.
So Kempe was laying the foundation for understanding how we can manipulate and interpret images mathematically.
Precisely.
Gotcha.
His work led to the development of invariant theory.
Okay.
Which is a powerful tool for studying geometric objects and their transformations.
Okay.
Now, fast forward to the mid-20th century.
Okay.
And you see these ideas starting to take root in the burgeoning field of computer vision.
So that's when the connection between geometry and computers really starts to emerge.
Exactly.
Which makes sense, since computer vision is all about analyzing and understanding images.
Right.
Which are essentially projections of the real world.
Right. As researchers started tackling the problem of how 3D scenes are projected onto 2D images, they realized that projective geometry and invariant theory were essential tools for the job.
So all this math that Kempi was working on was suddenly super relevant for making computers see.
It is.
That's pretty cool.
It is. And in the 1980s, researchers like Richard Hartley and Andrew Zisserman introduced the concept of the fundamental matrix. This matrix basically encapsulates the geometric relationship between two images of the same scene, taken from different viewpoints. Think of it as a bridge connecting the geometry of the real world to the images captured by cameras.
So the fundamental matrix is like a Rosetta Stone for understanding how 3D scenes get translated into 2D images.
Exactly.
Okay.
And it's deeply rooted in the invariants that Kempi explored decades earlier.
Right.
So you see there's this beautiful continuity of ideas with the work of early mathematicians like Kempi directly influencing the development of modern computer vision.
This is giving me a whole new appreciation for the hidden math behind everyday technology.
For sure.
It's like there's this whole world of geometry operating behind the scenes, making sure our cameras and computers can actually make sense of the world.
It's amazing.
Yeah.
And the paper we're discussing today takes all of this a step further. It really digs deep into this specific problem of figuring out camera positions in Flatland, using that fundamental matrix as a starting point and like expanding upon it in some really clever ways.
It sounds like this paper is a testament to the power of invariant theory.
It is.
And its relevance to computer vision.
Totally.
What really struck me is how the paper highlights this like growing complexity as you add more points to the scene.
Yeah.
It's like a delicate balancing act between freedom and constraint.
You hit the nail on the head.
Yeah.
You start with 4 points. And there's a lot of flexibility in where you can place the cameras.
Okay.
But as you add more points, the constraints tighten until you reach a tipping point. What's fascinating is that the paper shows that with 8 or more points, the problem actually becomes unsolvable.
Wait, so there's like a limit to how much information we can extract from images?
Yeah, there's a fundamental limit there.
That's kind of mind-blowing.
It is. But that's part of what makes this research so valuable.
Yeah.
It's not just about finding solutions. It's also about understanding the limitations.
This has been an incredible journey so far.
It has.
We've traveled through time.
We have.
Explored the foundations of projective geometry.
That's right.
And even glimpsed some of the hidden complexities of computer vision.
We have.
It's amazing how this seemingly simple question about camera positions in Flatland
I know, right.
has opened up such a rich and intricate world of ideas.
And we're just getting started.
Okay.
There's still a lot more to unpack.
All right, we'll lead the way.
Let's do it. Welcome back.
All right, so we left off talking about how the number of possible camera positions changes depending on how many points we're dealing with.
Right.
So let's start with the simplest case, just 4 points.
Okay.
In our Flatland world.
Right.
What does the camera center's variety look like then?
So with 4 points, one of the cameras is basically a free agent.
Oh.
It can be placed anywhere in Flatland and still capture the same image of those points.
Wow. So it's
like having complete freedom of movement.
Okay.
At least for one camera.
Gotcha. So what about the other camera though?
Right. So once that first camera picks a spot, the second camera's location gets locked down to a specific curve called a conic section.
Conic section. Now, are we talking like ellipses and parabolas and hyperbolas?
Yeah, exactly. Those classic curves from geometry class.
Okay.
And the type of conic that restricts the second camera depends on where that first camera is.
Gotcha.
And how the 4 points are arranged.
Okay.
It's a beautiful illustration of how geometry and constraints interact.
So we have one free-spirited camera and one camera tied to a specific curve.
Yeah.
What happens when we add a 5th point to the mix?
You bet it does. With 5 points, one camera can still chill out wherever it wants. But the second camera's position is now uniquely determined by the first camera's location.
So no more wiggle room for that second camera.
Exactly. It's like adding that 5th point creates a kind of lock and key mechanism between the cameras.
So it has to be in one very specific spot.
Exactly. And to figure out that spot, the paper uses this really clever visual method called the intersecting conic construction.
Intersecting conic construction.
Yeah, I won't get into all the technical details, but it involves using these things called cross ratios, which measure the relative positions of points to create 5 special conic sections. And all 5 of these conics intersect at a single point. And that point is precisely where the second camera needs to be.
So by understanding these geometric relationships, we can pinpoint the location of where that camera needs to be.
Exactly.
Okay.
And this construction isn't just some theoretical curiosity.
Right.
It has real practical value. It gives us a way to actually compute the camera positions, which is like super important for things like 3D modeling or robot navigation.
Okay, so 5 points brings in a stricter set of rules.
It does.
I'm sensing a pattern here. What happens when we bump it up to 6 points?
So with 6 points, the math gets a little trickier.
Okay.
But the core idea remains the same.
Okay.
The camera positions are still restricted, but now they're both confined to special curves called cubics.
Cubics, so like conics, but even more complex.
Think of them as conics, but on steroids.
Okay.
They can have more twists and turns.
All right, so now both cameras are dancing along these curves.
That's a great way to put it, yeah.
How do we even find these cubics, though?
Right, so the paper uses a combination of ideas from invariant theory and some classic algebraic geometry.
Okay.
Remember those Joubert invariants we talked about earlier?
Vaguely. Weren't those part of Kempi's work?
Exactly. Those were specifically designed for dealing with 6 points. Well, the paper cleverly uses these Joubert invariants along with some special equations called the cromona hexahedral equations.
Wow, that's a mouthful.
It is to derive explicit formulas for these cubic curves.
So even though the math is getting really complex, they still provide concrete ways to figure out where those cameras need to be.
It's a beautiful example of how these seemingly abstract mathematical concepts can be applied to solve real-world problems.
Okay, before we jump into 7 points, something's been bugging me.
Okay.
We keep talking about these conics and cubics as if they're these fixed universal objects.
Right.
But don't they depend on the arrangement of the points in Flatland?
That's a great question, and you're absolutely right. The shape and location of these curves are directly tied to the specific set of points we're looking at.
Gotcha.
If you were to change the points even slightly, those curves would shift and morph as well.
So each set of points creates its own unique geometric landscape.
That's a great way to think about it.
With its own conics and cubics.
Yeah, each scenario has its own unique set of rules.
Okay.
And this has important implications for real-world applications.
Okay.
You know, when designing computer vision algorithms, we have to keep in mind that the input data, those points, will always have some degree of variation and uncertainty.
Right.
So our algorithms need to be robust enough to handle those changes without falling apart.
Right, they can't be too sensitive to those variations.
Exactly.
This conversation has added a whole new layer of depth to my understanding of the camera center's variety.
Yeah.
It's not just about finding these abstract curves, it's about recognizing how they're linked to the actual data points.
It's a dynamic dance between points and curves.
Okay, I think I'm ready to tackle 7 points. What new challenges and insights await us?
Get ready for a real mind bender. Because 7 points is where the camera center's variety story reaches its climax.
Ooh, okay, I'm excited.
The paper shows that with 7 points, the number of possible camera locations shrinks dramatically.
Okay.
In fact, there are at most only 3 possible spots for each camera.
3? That's a huge drop.
It is. It's like all those possible camera positions suddenly converged into a tiny handful of options.
Wow.
And the way the paper finds these positions is really elegant.
Okay.
Remember those cubic curves we talked about for 6 points?
Yeah, those are the ones that look like supercharged conics.
Right. Well, they make a comeback for 7 points.
Okay.
But with a cool twist.
All right, lay it on me.
For every set of 6 out of those 7 points, you can create a corresponding cubic curve.
Okay.
Using the methods we talked about earlier.
Okay.
And since we have 7 points total, that means we end up with 7 cubic curves.
Okay.
7 cubic curves, each representing a different perspective on those points.
It's like a geometric symphony.
I love that analogy.
Yeah.
And here's the kicker.
Okay.
All 7 of those cubic curves intersect at the same 3 points.
Whoa. So all those different perspectives suddenly align at those 3 special locations.
Precisely. And those 3 points of intersection are precisely the only possible spots where the cameras can be.
So we pinpointed those exact spots for 7 points.
Yeah, it's a beautiful demonstration of how geometry and invariant theory can reveal these hidden connections and constraints.
And this result has practical implications too, right?
It does. For computer vision algorithms, it means that when dealing with 7 points, the search space for camera positions becomes much smaller.
Okay.
Which can save a lot of computational power.
It's like geometry gives us a shortcut.
Exactly.
Guiding us toward the right answer.
And this highlights the importance of understanding the underlying mathematical principles behind computer vision.
Absolutely.
It's not just about brute force computation. It's about using elegant geometric insights to create more efficient and effective algorithms.
This exploration of the camera center's variety has been truly mind-blowing.
I know. It's amazing, right?
It is.
How the geometry of projections just dictates the rules of the game.
Yeah.
Setting limits on what's possible.
Yeah, and the paper's ability to weave together the algebra, the geometry, the computer vision.
I know, it's remarkable.
It really is.
Where do we go from here?
I know 7 points feels like a pretty satisfying stopping point.
It does, doesn't it? But hold on to your hats.
Yeah.
Because the story isn't over yet.
Okay.
There's one more twist waiting for us.
All right, I'm ready.
And it involves what happens when we dare to venture beyond 7 points.
All right, so 7 points felt like we were hitting some kind of limit. What happens when we try to add even more points?
So with 8 or more points,
okay,
things take a dramatic turn.
Oh, okay.
The camera center's variety just disappears.
Disappear. So you're saying like
it's gone.
There's no camera position that would work.
Yeah. No matter where you place the cameras,
Okay.
you won't be able to get those points to project onto the same image.
So there's a fundamental limit to how much information
Yeah.
we can extract from images.
Right. The geometry is like, nope, you've gone too far.
And this has implications
Big implications.
for computer vision.
For computer vision.
Right.
Like if you're trying to build a 3D model of something
Yeah.
based on 2D images and you have more than 7 corresponding points,
Okay.
you can't rely on the camera center's variety to guide you.
So all those 3D scanning apps and stuff?
Right. They must be using some pretty clever tricks to get around this.
I guess so.
Yeah.
It really highlights the importance of understanding these fundamental geometric constraints.
It does.
It's not enough to just throw a bunch of data
Right.
at an algorithm and hope for the best.
No, we need to know the limits.
We need to know what's possible
What's possible.
to develop algorithms that are going to work.
Yeah, robust and reliable,
Yeah.
even in challenging scenarios.
This has been a really incredible journey
It has been.
through projective geometry and computer vision.
Yeah, who knew a geometry could be so exciting?
I know, right? We started with this really simple question
Yeah.
about cameras in Flatland.
Mm-hmm.
And we've uncovered all these really profound insights
Yeah, it's a great example
about the limits of image formation.
of how seemingly abstract math can have really concrete consequences in the real world.
I've gained a whole new appreciation for geometry.
Me too.
It's not just about shapes and angles.
Yeah.
It's about how we perceive and interpret the world.
It's about the fundamental relationships.
Yeah, and all these geometric principles are going to be even more important
Absolutely.
as we keep pushing the boundaries of computer vision and AI.
For sure.
Well, I think it's time to wrap up our deep dive
Okay.
into a computer vision problem in Flatland.
It's been a pleasure.
We've uncovered some really fascinating insights. And I hope all of our listeners have a new sense of wonder about the mathematical beauty of the world around us.
For sure.
So that's it for this episode of The Deep Dive.
Until next time.
Don't forget to check out the link to the paper in the show notes.
Yes, definitely do that.
And we'll see you next time
Yeah.
for another deep dive into the world of science and technology.
Okay. Sounds good.
Until then, keep exploring.